All right. Hello. How's everybody doing? Guys? How's everybody doing? I hope you guys are good. Um, yeah. So this is the other platform, or let me say the other TikTok page that I am utilizing. The one I actually like put up because in case of backup, in case I need an alternative platform to be able to do live lessons, this is it. And what I like about it is that it's fairly new, so not too many people know about it, and the whole point and purpose is so that I can actually get a bit of privacy away from from all the popularity that's actually happening with the other channel. It's become too overcrowded, if you want to put it that way. Guys, I want to actually do grade 10 functions with you. I think that's one topic that I see is kind of in need of a little bit of attention. So I'm going to hop through a couple of questions that are functions related for grade 10s. So if you want to share the live with like other grade 10 friends that you have, please do go ahead so that they can have the opportunity of actually hopping onto the session and hopping onto that. Finish the parabola. Okay, do you still remember what it is that we were doing with the parabola? Maybe that's I mean, we could always finish the parabola, but yeah, thing is that's still remember? Let's do this. All right, so let's do like this. Let's do this. Okay, let's just recap on it then. I thought the parabola we had actually kind of done and completed it. I was under the assumption that we did. Okay, so grade 10 parabola. So the parabola form is y is equal to ax squared plus 2. All right, that's the form of our parabola. Y is equal to ax squared plus 2. Remember, for y, okay, y can also be represented in function notation, and that function notation, f of x, g of x, l of x, p of x, I mean, it can be any other letter of the alphabet of x, So yeah, that's just a little bit about that variable. So y is equal to ax squared plus 2. Remember, we said a, when a is positive, meaning the coefficient of x squared, exactly, Lerato, but let me just recap on it anyways. So if you remember with the parabola, and remember, you can always go to the YouTube channel and actually check out what we did previously in the other sessions. Okay, so with the parabola, y is equal to ax squared plus 2, right? A is positive, we said that is the shape. Okay, that is the shape. Okay, and in grade 10 your parabola is always symmetrical along the y-axis. Okay, always symmetrical along the y-axis. It's like the y-axis is the line of symmetry. So the equation of the axis of symmetry is x is equal to 0 for your parabola. Okay, so a is greater than 0, we smile, or we concave up. A less than 0, we said we are sad, right? Concave down. Okay, right? Yeah, so that's just something to note there with the parabola. Then our q value, all right, the numerical constant that usually is represented here, our q value, it is basically our y-intercept And remember, by y-intercept we mean where the graph cuts the y-axis. So y-intercept, and also it is the turning point. All right, yeah. So in grade 10, your Q value tells us about where the graph cuts the y-axis, and it also tells us about the turning point, where the graph turns. Okay, and remember, when A is positive, you know, like I said, it's a smiley face. That means it's concave up, so that means we have a minimum value. Whereas if it's A is less than 0, we have a concave down or a sad face, and we have a maximum value. Okay, so there's a max here, maximum value, whereas when A is less than 0, we have a minimum value. Okay, minimum. So our Q value tells us what the maximum or the minimum value will be. Okay, so this Q value plays it actually is something quite significant, but also furthermore, we also talk about vertical shift. Okay, Q, what does it do? It affects the movement of the graph. So what does Q do as well, this Q value, besides what it is? So what is it? Because what we just defined here is what is it. So what is Q? Q is the y-intercept. It is also the turning point. What does it do? Okay, so what does it do? It actually affects or influences the graph's movement up and down. So vertical shift moves up, the graph moves up whenever Q is greater than 0. Okay, and the more you add values to Q, that means you move the function, the entire function up. But then if Q is less than 0, or you subtract 0, then if Q is less than 0, it means that the function moves down. Okay, I hope that makes sense. So the Q greater than 0, movement of the function up. Q less than 0, movement of the function down. Okay, so hopefully we are hammering sonke and no one is salarying. Okay, usalelani sihamba sonke. If everybody is with me and we are together, I hope we are together. So I'm going to rephrase this again. The parabola function or the quadratic function has the general form y is equal to ax squared plus 2. How do we know it's parabola or quadratic as a function? Guys, the variable x has to be raised to the power 2. That's what makes it quadratic. Okay, so x squared, we know that when it's x squared, it must be a parabola, and this x squared must be in the numerator of our function. Okay, the coefficient of x squared, a, tells us something about the shape of the function. Okay, so when a is greater than 0, we know we have a smiley face, concave up. This is the shape of the function. Okay, when a is less than 0, which means when it's negative, okay, it is a sad face or a concave down shape. Okay, then we have this Q value here. Okay, this Q value tells us what is it? It is the y-intercept. In other words, it is the value that tells us where the graph cuts the y-axis. Okay, where the function cuts the y-axis. That's what the Q value is. It is also, secondly, the turning point, TP, meaning turning point, where the graph turns. All right, where the graph turns, whether it's smiling because a is greater than 0, where it turns. Okay, the minimum point of the function. When a is less than 0, where it turns, the maximum value of the function. Okay, the Q value. So this Q value, y-intercept, turning point, maximum when a is less than 0, minimum when a is greater than 0. Then our Q value, what is it? Our Q value, we spoke about the fact that it's the y-intercept, it's the turning point, it's the maximum or the minimum value depending on which value of a we are looking at. Then what does the Q do? What does it do? Okay, it affects or influences the graph's movement up and down. Okay, when Q is greater than 0, movement up. It shifts up. The entire graph moves up. However many units Q is. And then if q is less than 0, then we're talking about the graph's movement down. Okay, does that make sense? I hope it makes sense, guys. So that's very, very important, all right, that we understand that. All right, then something else I just want to quickly speak about is the idea of domain and range of a parabola. Okay, so if a parabola function, all right, is a concave up like this, or smiley face, all right, domain, what is the domain of any function? The domain of any function is the x values where the function exists. We are looking for the x values where the function will exist. Okay, the values of x where the function exists. That's what we call the domain. All right. On the other hand, we have something called the range. What is the range? The range, unlike the domain, is the y values where the function exists. All right. Okay, so I repeat, domain is simply the x values where the function exists. Now, when we talk about x values, guys, on the Cartesian plane, we are looking left to right. Left to right. So we're looking at the function from the left to the right. From the left to the right, to the left to the right, from the left to the right. That's what domain is. Okay, because x values, if you look at the Cartesian plane, let's just observe something about the Cartesian plane. This is called the x-axis, all right? This is the x-axis of our Cartesian plane, all right? This is basically the platform where we can sketch all of our graphs. We can sketch all graphs that we know are in existence on a Cartesian plane so that we can see what the visual image of each graph looks like. Does that make sense? So on our x-axis, which the x-axis is from left to right, okay, there is a number line. Okay, the number line here at the origin, the number 0 is represented. Then we would have all negative values on the left hand side of the x-axis, and then we'd have all positive values on the right hand side of the x-axis. So hopefully we are together there. And please, guys, these are real numbers. In other words, all rational and irrational numbers can be represented on the x-axis. So hopefully we all understand when I say real numbers. Guys, do we all understand? When I say real numbers, do we all understand what real numbers are? As grade 10 learners who are going to be writing paper 1, you should all understand what a real number. What is a real number? All right. And then as a result, you should understand that real numbers are basically made up of both rational and irrational numbers. Okay. Okay. And then if you look at rational numbers alone, you can further subdivide rational numbers into whole numbers, integers, and natural numbers. Let me just check in the comment section. Maybe you guys can comment for me there in the comment section. What is a integer? What is an integer? Okay, whilst you guys are commenting in the comment section, you're finding your mojo to type. All right, I want you to comment, what is an integer? What do you understand an integer to be? Okay, whilst I write numbers here, you can let me know in the comment section. Hopefully I have people that are alive and who are existing that can actually talk to me and comment in the comment section so that I can know that you guys are here, you are listening. What is an integer? What is an integer, guys? Do we know? My comment just got removed. Okay, I don't understand why it got removed. Lera Toshem, man. Okay, the thing is, it's the first time I'm going live on this. And the thing is, okay, all right. So I see that not that guy says or numbers that go up to infinity. Okay, a number that can be negative or positive, for example, -2, -1, 0, 1, 2. Okay, guys, integers. Okay, hopefully you all know the symbol that they usually use for integers is this Z. All right, it stands for integers. And rightfully said, integers are positive and negative whole numbers. All right, they go from negative infinity to positive infinity. Those are negative and positive whole numbers. So here I've just represented a limited example of what integers are. Okay, so for instance, 0, 1, 2, 3, 4, 5, these are positive whole numbers. All right, 0, 1, 2, 3, 4, 5, but we can extend it to -1, -2, -3, -4, -5. These guys are just a limited number of integers that we have. Okay, so if you look at 0, 0 is an integer. If you increase your numbers by 1 to the right and you decrease your numbers by 1 to the left, those are all integers. They go up and down by 1. Those are your integer values, and they can be negative or positive. So it's all the way to negative infinity, meaning we go on forever in the negative direction, and all the way in the positive direction. Those are what we refer to as integers, your positive and negative whole numbers. Okay, they increase and decrease by 1. Okay, so if I ask you, is 12 an integer? Okay, is 12 an integer? Can you guys let me know in the comment section, yes or no? Is the number 12 an integer? Yes or no? So 12, is it an integer, guys? All right, so I love the fact that you guys are saying yes. That's beautiful. Now I want to ask this question: is 6/2 an integer? Okay, so yes, 12 is an integer, but is 6/2 an integer? Okay. All right. Okay, now I see what you guys are commenting. Like, let's look at this number, 6/2. Now 6/2, right? We need to first check, is this simplified? All right. So if it's not, then the question is, what's 6/2? 6/2 is like saying 6 divided by 2. What's the answer? The answer is 3. Oh, now do you want to answer the question? Is 6/2 an integer, guys? I am asking you again. Okay. Here's an opportunity for redemption. Okay. Is 6/2 an integer? Okay, so okay, yes, I know you said yes, and I'm very proud that you did, because it means that you see beyond just what is apparent from the eyes. Because I think most of you looked at 6/2 and you're like, hi, it's a fraction, so it can't be an integer. But you see, the thing is, guys, when you make a judgment of a number, you must first check, is it simplified? And after simplification, then you can comment. Okay? After simplification. Okay, after simplification. Okay, so very good, okay, I'm very proud of you, good job. Okay, so yes, please, this is an integer. Okay, 6/2 is an integer. This there at the top, the 12, is an integer. All right, guys, my network is fine, so if there's any problems with the network, it must be your guys' side, because at the moment what I'm seeing is beautiful, good connection. Okay, beautiful, good connection. I'm gonna ask another question. Is -25/5 an integer. Oh, okay, now it's bad. Okay, now it's bad. Now my network has gone south. Just check it out again. Yeah. Oh my soul. Okay, my network is doing the rounds, doing funny stuff. Ish. Okay, guys, how's the network now? My network is really playing. It's not loyal. It's not loyal at all. Guys, how's my network? How's my network? Okay. Okay, so maybe the silence is an indication that the network is really that bad. It's laggy, ish. Yeah, perish. Yeah, you see, that's the thing, okay, guys. Unfortunately, this is the one nemesis, one enemy. You know, the unseen enemy is network. It works against every single effort one makes to try and go on these live sessions. All right, but I see you guys did comment. Is negative 25 over 5 an integer? You guys seem to say yes. And yes, guys, what did we do? We went ahead, we asked ourselves, is negative 25 over 5 simplified? Obviously not. When you simplify it, we get negative 5. And we all know that negative 5 is actually an integer. So please, guys, let's make it a point, even as you guys are preparing for paper 1 and you guys are looking into making sure that you have mastered the content, make sure that with all numbers you are able to verify the number. Don't just look at the number and judge it. You know, this is like what we do with people that we meet each and every single day. We just take one look at them and we make a conclusion. We're like, I suka, that person is a bad person. And what we need to do sometimes is get to know a particular person. Then we find out, oh my goodness, we have a golden individual here. So she actually is not what I thought she was. She actually is, you know, this amazing, wonderful individual, you know. And yeah, it was just judgment from the outside. Okay, so that's just something to note here, that let's make sure that after simplification we make our judgment. In other words, after taking a look and making further investigations, let us make sure we make our conclusion about a number after that. Does that make sense, guys? Are we clear on that? Am I making sense to you guys? Because if I'm not making sense, you must indicate there in the comment section. But if I'm making sense, then please, you must also say so. Okay, thank you, Kay. Appreciate it, Kay. Appreciate you, Kay. Now, so those are integers, all right? Then, like I said, there are also what we call natural numbers. Do you guys know what natural numbers are? Okay, maybe let's start at whole number. Do you guys know what a whole number is? Now I'm just doing a bit of revision as well on other things whilst I'm simultaneously attending to functions. Know what a whole number is? I have a feeling it's network. Yes, Lerato, very true. Okay, so whole numbers. Whole numbers. So whole numbers are numbers. We have this symbol that we use for whole numbers, the N with the O. It's like it's saying no. And obviously, since there's that 0 there, it means it's numbers that start from 0. Okay, they increase though by 1. In other words, they go up by 1. Okay, and they go up by 1 until where? Until infinity. All right, so basically they increase by 1. So from 0, we can obviously look at 0, we say 0, 1, 2, 3, 4, 5, 6, and so forth. Okay, so those are whole numbers. Let's move on. What are natural numbers? I think you guys are on a roll there. What are natural numbers? Natural numbers. Okay, Loretta says numbers that start from 1. Very good. Yes, they start from 1. And they increase by 1. That's very important. They increase by 1 until infinity. Okay. They increase by 1 up until infinity. So very important. Very, very good. Then what okay, we've got natural number, we've got integers, we've got whole numbers, we've got natural numbers. Let's look at what are rational numbers. Let's see if we've got a working definition there. What are rational numbers, guys? Rational numbers. What are rational numbers? Rational numbers. Not that guy Kex says numbers without a decimal. Without a decibel. Decibel. Okay, I think that's a new word I'm getting from you. You're gonna have to enlighten me there about decibel. Mbali says numbers that can be written as a fraction. Very true. Numbers that can be written as a fraction. There are certain conditions there about that fraction, which I'd like you to explain more. Okay, numbers that can be written as a fraction. So in other words, you're trying to say to me, Mbali, that if I have the square root of 3 over 4, I think this is a fraction, by the way. The square root of 3 over 4 is a fraction. The square root of 3 over 4. So are you saying to me, this is a rational number? The square root of 3 over 4. This is a fraction, by the way. Okay? It's a fraction. Okay? Lerato is saying numbers that can be written as fractions, but terminates. But terminates. New words. What's that? What does terminate mean? Okay. It seems like you're speaking like about Terminator, you know, the return of Terminator. It's like a movie that you're referring to here. Right. So that's why I'm saying, guys, that like I cancels. Okay, all right. I like that. Okay. So let's start at the basic. So rational numbers are numbers that can be written, as you guys said, they can be written as a fraction. But let's explore this fraction. Let's say the fraction is a over b. The a, we are told, is supposed to be an integer value. Now, we just spoke about what integers are. Integers are positive and negative whole numbers, which increase and decrease by 1. So we have an idea what we are referring to when we are talking about integers. So in other words, what they are saying here is that the numerator needs to be an integer, and the denominator, which is b there, also needs to be an integer. But then there's a condition that the denominator cannot be what? Cannot be 0. We can't have 0 in the denominator. All right. So three conditions. A must be an integer. B must be an integer, meaning the numerator and the denominator of our fraction must be both integers. That's why, for instance, when we come here and I ask you, is this a rational number? Well, let's look at the numerator. Is this an integer? Is the square root of 3 an integer? That's the million-dollar question, and I'm sure you guys can see that this is not an integer. Is 4 an integer? Yes, it is an integer. So does this fraction then qualify as a rational number? Does this square root of 3 over 4 qualify to be called a rational number? Exactly, Renato. No, no, no. Okay? Okay, I hope it makes sense, guys. Right? So a rational number, I repeat, is a number that can be written as a fraction. The numerator and the denominator of that particular fraction must both be integers. So we must have integer values. What are integers? We just learned not so long ago that integers are positive and negative whole numbers. They increase and decrease by 1. So if it's 0, if it's 1, if it's 2, if it's 3, if it's 4, if it's 5 in the numerator, we are 100% good. Okay, if it's 1, 2, 3, 4, 5, or -1, -2, -3, -4, -5 in the denominator, we are good. But there's a condition that in the denominator, we cannot have the number 0. All right, and there's a reason why we can't have the number 0 in the denominator, and I'm waiting for you in the comment section to let me know. Why can't we have the number 0 in the denominator? Do you know, guys? Why can't we have the number 0 in the denominator? What does it mean for the fraction? If we have 0 in the denominator, what does it mean for the fraction? What trouble do we run into if 0 is in the denominator? Thank you, Lerato. Okay, the fraction will be undefined. So trying to avoid 0 in the denominator is us trying to make sure that we do not find ourselves in a situation where our number is undefined. So we try by all means to make sure that 0 is not found where? In the denominator. Okay. Now maybe for the hyperbola function, you'll now understand why it is that with your hyperbola function, all right, so since we are on this point, your hyperbola function in grade 10 has a variable x in the denominator, okay? And we know that we cannot have x being equal to what? To 0. Hence, in grade 10, you have something called a vertical asymptote, all right? And your vertical asymptote is simply the vertical line where the function does not exist. Okay, and where does it not exist for your grade 10 hyperbola functions? It does not exist. The function does not exist where x is equal to 0. Okay, what's the new word added to your dictionary? What's the new word added to your dictionary, Lerot? New word added to my dictionary. I wonder what that word is. Let me know in the comment section. What new word is that? Vertical what? Vertical asymptote. Vertical asymptote. Okay. Remember your hyperbolas, your hyperbola function is one of two functions that have what we call an asymptote. It is the only function that has a vertical one though. All right. What is an asymptote? An asymptote is simply a boundary line where the function will never ever touch. So for instance, your grade 10 hyperbola never touches the y-axis. It never cuts through the y-axis. It never does, because your asymptote ensures that your function is within that a certain boundary, and it does not touch that boundary line. Okay, that's why in one of my videos there in the other page, my maths is a game page, I actually did a video there where I said but I spoke about something that has to do with asymptotes, and maybe when I get to hyperbola functions just shortly, I'll share that with you. But guys, this thing of 0 not being in the denominator, so important. Thank you so much, Leta. No, thank you. So this thing of 0 in the denominator, we have to avoid. Okay, so I hope you understand now why we say a rational number is a number that can be written as a fraction, where the numerator and the denominator are both what? Integers, and where the denominator can never be the number 0. Okay, and then Lerato mentioned something about if we look at the decimal numbers, the decimal number of a rational number, there are two forms of the decimal number that we find for rational numbers, and the first one is your terminating decimal number. All right, and then the other one is your recurring decimal number. Okay, terminating and recurring. Terminating has to do with after the comma you have a few numbers, right? It has to do with rounding off, terminating decimals. Okay, so if your number is rounded off to 2 decimal places, you're going to see 2 numbers after the comma, and it stops, it cancels, the number stops existing. There are no more numbers after 1, because it's canceling at the second decimal place. That's what terminate means. All right, so 0.51, stop, cancel, second decimal place, that's a terminating decimal. Now you can stop your decimal at your 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. All right, whatever decimal you decide to round off to, where you round off to is where you terminate. All right, yeah, these numbers after the comma don't go on forever. They stop, they cancel, they terminate. Okay, I'm sorry, I'm going to use a very crude example. Sometimes young girls will fall pregnant, and they will fall pregnant not wanting to fall pregnant, and usually some of them will basically take the route of doing what to the pregnancy. They will terminate the pregnancy. What happens when you terminate a pregnancy? When you terminate a pregnancy, it means you're bringing it to a stop. The baby was developing, or the fetus was developing, but then maybe at a certain point you decide to stop that. Okay, so hopefully that's not something that we find ourselves being in the situation of, but what I'm saying is it's just to try and sort of like emphasize this point of terminating decimal. All right, yeah, I know, like I said, it's a crude example, but you know what, sometimes this gives me an opportunity to talk to my learners at school and really encourage them against activities that would lead to such a situation, especially as young learners that are still in an academic journey, or still trying to form and forge their own mindsets and views about life and so forth. What you'd like to do is want to protect your sense of being a child, so that you do what you need to do. So yeah, just that example, guys, terminating decimal. Right, so these are decimals where the numbers, they stop at some point. They're not going to go on forever. But look at recurring decimals. Recurring decimals, on the other hand, they have repeating, because the word recur means repeat. What are we repeating? We are either repeating a particular digit forever, infinite. Okay, so I like this, repeating forever. Repeating forever. Imagine eating sweets forever. Breakfast sweets, lunch sweets. You repeat forever. Yeah. So I hope you understand. So the dot at the top of the 1 indicates repetition. Sometimes instead of a dot, they use a line above the numbers that are supposed to repeat. So here we are repeating a single digit, 0, if you were to write it down, it's like 1, 1, 1, 1, 1, 1, 1, but it goes on forever, the 1. Okay, it doesn't stop, no terminating. Okay, or with this case where you're having 2 digits repeating, 0, 2, 5, 2, 5, 2, 5, 2, 5, forever and ever. All right, so guys, please note that they use a dot on top of the number, or they use a line above the number to indicate the repetition. Okay, all right, so I just wanted to touch on that part. Those are rational numbers. So if you look at your x-axis, sorry guys, I know I deviated a bit, but I just needed to explain that part. When you look at your x-axis on your Cartesian plane, these are x values, but I want you to understand these x values, they are real numbers, okay? Real numbers, both rational and irrational numbers, because remember, irrational numbers are the opposite of what rational numbers are, okay? They all exist on the x-axis, okay? Yeah, it's just that like I'm not revealing every single number between 0 and 1, but I hope you understand that this number line, this x-axis, is encompassing all real numbers, all of them, okay? All real numbers. Then we have a y-axis, and above the x-axis, the y-axis has positive values of y. Then below this x-axis, the y values are negative. All right? So this is from the bottom, your negative values, to the top, your positive y values. And obviously this y-axis can go on to infinity. I mean, this y-axis goes on forever, all right, to the top. And then this y-axis at the bottom here with the negative values, it goes on forever. So that means there are negative infinity, if you will, in this direction for y. So y is represented from the bottom to the top, started from the bottom to the top, bottom to the top. Then your x-axis is from left to right, okay? Right. So all of this explanation was all in the name of doing what? Of emphasizing. We said, what is the domain of a function? The domain is the x values where the function exists. And we look at the domain from left to right. Why do we look at it from left to right? It's because that's where the x-axis exists. Are you with me? That's where the x-axis exists, and the x-axis has its numbers negative and positive from the left to the right. Then if we look at the range, those are the y values where the function exists. So we're looking at the y values where the function exists, your smallest values, your negative values, from the bottom all the way to the top. So bottom to top, that's how we read the range for your function. So the minute you sketch a function on your Cartesian plane, you can always tell me what the domain of that function is, meaning where does it exist from left to right. Are you with me, guys? Where does the function exist from left to right? That's the domain of a function. Then the range, the y values, where the function exists. Now you look at it from the bottom to the top, and basically the direction matters, guys, that we look at the range from the bottom, your smallest values, to the top, your biggest values, from the left, your domain, smallest values, to the right, biggest values. You see, we're always looking at these domain and the range from the smallest to the biggest. So for domain, left, which is the smallest, to the right, your biggest. Range, from the bottom to the top. Y values from the negative to the positive. All right, so hopefully that makes sense to you guys and you understand what I mean by that. Okay, all right, that is a little bit on your parabola. All right, your parabola function. Okay, and I mean we'll look at some examples, but this is the theory, guys. These are the concept. The concept of the parabola is basically understanding your a value, what it is, what it does, your q value, what it is, what it does. Okay, and then yeah, from there you should be able to answer questions, which I'll be looking at just shortly. Okay, I have a buffet of questions that I'm gonna go through with you guys just now. Okay, now let's look at the hyperbola. Okay, we already kind of like alluded to the hyperbola, but let's look at it, the hyperbola. What is the form of the hyperbola function? The form is y is equal to a over x plus q. Okay, y is equal to a over x plus q. I repeat, y is equal to a over x plus q. A. Now, our a value, what is it? our a value will also give us the shape and the position of the function. So when a is greater than 0, our hyperbola function, now this here for the hyperbola function will always represent the y-axis, whose equation is x is equal to 0. And then this here is called our horizontal asymptote. Okay, guys, there's a deliberate reason why I'm actually drawing in our horizontal asymptote instead of the x-axis. Okay, because I spoke about earlier on the fact that we have two things that are new with our hyperbola. We have something called the vertical asymptote. What is this thing here? Okay, vertical asymptote. All right, vertical asymptote, I'm gonna just speak about the word asymptote. An asymptote is a boundary line where the function does not exist. Okay, so asymptote is a boundary line where the function does not exist, does not touch. Okay, that's what an asymptote is. An asymptote is a boundary line. Okay, and this boundary line, guys, is usually, okay, if it's the vertical asymptote, the boundary line is kind of drawn with spaced out lines. Okay, you can see these spaced out lines. It's not a solid line, but it's spaced out lines. Okay, so VA means vertical. Vertical is from the bottom to the top. So this vertical line, this vertical asymptote, all right, is what basically, this is how we would represent it. Then we have a horizontal asymptote as well. Okay, horizontal asymptote. So we not only have a vertical asymptote where the hyperbola is concerned, but we also have a horizontal one. Okay. Okay, so this is very important to note, and I'm going to explain everything there is to know about this. But let's go back to the function. So I said the function for hyperbola is given by the y is equal to a over x plus q. This a is in the numerator, this x is in the denominator, plus this q. This is a q value which is in the numerator, so it's q and it's a representation of some constant value. So what I said now is that when a, meaning the value that is in the numerator, is greater than 0, there's something that we note, and that is the function will be found in the first and third quadrant. Okay, now something to note that's very important is that your first and your third quadrant, these quadrants are defined by the boundaries, the VA and HA. In other words, the horizontal asymptote and the vertical asymptote. So that's why I was saying to you guys that if I am to indicate the boundaries for the hyperbola function? First and foremost, I would say that the first boundary, which is the vertical asymptote, is indicated by the value of x in the denominator that we know we should not be having in the denominator for any fraction. And what is that value, guys? What is that value that x cannot be in the denominator? Right? What is that value that x cannot be in the denominator? Right? Okay, not that guy, okay, 0, right? So we say that our vertical asymptote, since we know that x cannot be 0, we say that our vertical asymptote for the hyperbola function, and guys, in grade 10, this is always the case, always. So as long as you are a grade 10 learner in South Africa, the vertical asymptote will always be defined by the equation x is equal to 0. Why? Because we know that x shouldn't be 0, because if this fraction is having 0 in the denominator, that's what we know, that this cannot exist. It cannot be defined. So we say x is equal to 0 is our vertical asymptote. Okay? And remember that x is equal to 0 is simply an indication of some vertical line which cuts through the origin. So that is why x is equal to 0 in actual fact is the what? It is the y-axis of the Cartesian plane. This x is equal to 0. It is the y-axis. The vertical line, which is the y-axis, is the line x is equal to 0. Hey, I hope we are together here, guys, and I hope you are feeling me very strongly, because these boundary lines are extremely important. This hyperbola function is unique because in order for it to exist, it exists within the boundaries of the boundary lines. If the boundary lines are not there, this function cannot exist. But when the boundary lines are in place, then the function comfortably is able to exist. So I said the first boundary line, or the first asymptote that we need to indicate very strongly, is the vertical asymptote, which is defined by the equation x is equal to 0. Why? Because our denominator cannot be 0. Because if it is, then it means that this fraction, and in actual fact the entire function, cannot exist. So we first indicate the vertical asymptote. X is equal to 0, which is the y-axis, and this is always, what did I say, guys? This is always the case in grade 10. It will not change as long as you are a grade 10 learner. In grade 11, we are going to reintroduce this function, and then when we take it up the next step, we are going to then indicate that, oh, because of these changes, now we can say that the vertical asymptote can take on a new form. All right, but for now in grade 10, this x value is single in the denominator. X cannot be 0 only here, because that would make the fraction undefined. So we say the vertical asymptote in grade 10 is x is equal to 0, the y-axis. Okay. Okay. I hope we are moving together. You feeling me, guys? Are we happy so far? We good? Right. Now, look. The next thing is our horizontal asymptote. The HA, the horizontal asymptote. Remember, I spoke to you about the vertical asymptote. Now, the hyperbola does not just have a vertical asymptote alone, it has a horizontal asymptote. How do we get that horizontal asymptote? We get it from the Q value. The Q value as it is. You see this Q value, guys, as it is the horizontal asymptote. So whatever value might be there, if this Q value is equal to 3, then we know that our horizontal asymptote is 3. If this Q value is -7, then it means our horizontal asymptote is -7. But the equation would be y is equal to that Q value. whatever that Q value is. So generally speaking, we are just going to say y is equal to Q because we are looking at a general function. But if we had a specific number there in the place of Q, then we would say y is equal to whatever that value is that was supposed to be in the place of Q. If it's negative, we write that negative number. If it is positive, we write that positive number, because the Q value as it is gives us the horizontal asymptote whose equation will be y is equal to whatever that Q value is. Hey, I hope you are feeling me here, guys. Hey, I hope you are feeling me. So two asymptotes. X is equal to 0, which is the vertical asymptote, and then y is equal to Q. Or remember, we will specify that specific value for our horizontal asymptote. Okay. Now, when we have the vertical asymptote, which is the y-axis in grade 10 all the time, like I said, which equation is x is equal to 0, and then we have the horizontal asymptote, which is y is equal to Q, then, Jonga, look at this. This is our first quadrant. This is our second quadrant. And I'm sure, guys, you can see the boundary of the first quadrant. Okay, the first quadrant is limited to this space because this boundary and this boundary keeps it in. First quadrant, second quadrant, third, fourth. All right. So these are our quadrants based on the vertical asymptote and the horizontal asymptote. So what did I say to you guys about A when A is greater than 0? I said to you that your hyperbola function, the arms of the hyperbola function will be found in the first and the third. So the odd number quadrants. The odd number quadrants. Hey, the what? The odd number quadrants is where your function will be found the minute the value of A is one that is greater than 0. Meaning in this quadrant and this quadrant. That's where your function will be found if A is greater than 0. So say then, what does it mean then if A is less than 0? Where do I find the function? Do you guys want to tell me where I would find the function if A is less than 0? Remember, this will be my vertical asymptote. Then I will have whatever horizontal asymptote, y is equal to whatever that value of Q will have been. Very good in the comment section. I love you guys. I love you too much. I love you. I love you. I love how you guys are able to flow. So with that, when A is less than 0, we are talking about the function being found in the even number quadrants. Make sense? Even number quadrants. All right. We are flowing together. We are flowing together, guys. We are flowing together. We are feeling each other, which is good. So, yes, man. Yes, man. Yes, man. Yes, man. Yes, man. Yes, man. Okay. All right. Okay. Then, I've told you what A is. A is simply the thing that's going to help us understand where the function is found and its shape. And then Q, I told you what Q does. Q gives us the value of the horizontal asymptote. I mean, I told you what Q is. But now you might want to know, what does Q do? Q does same thing, guys, that it did with the parabola. It is involved in vertical shifting. If Q is greater than 0, we're moving up. If Q is less than 0, we're moving down. All right? Because you can imagine, if this is the horizontal line, the minute we add to the Q value, we're moving up. We're moving the entire function up. The minute we subtract Q, we're moving the entire function down. So you see, Q seems to be involved in vertical shifting, whether it's a hyperbola function or a parabola function, and even your straight line function, and even your exponential function. Your Q value is always involved. What does it do? It moves things up and down, up and down. If it's positive, we're moving up. If it's negative, we're moving down. If we're subtracting from the Q value, we're moving down. If we're adding to the Q value, we're moving up by however many units has been indicated. All right, so I'm sure you guys now want to be like, okay, now say I see we get it, thank you very much, that was nice. So all in all, in summary, say you are saying that this hyperbola function is very easy. Yes, that's what I'm saying in short. I'm saying the function that's the hyperbola has its y is equal to a over x plus 2. Please take note the form. The x variable is in the denominator, okay, and it's raised to the power 1. That's what makes it unique, the hyperbola function. Then, like I said, it has 2 asymptotes. That's what makes this function unique. It has 2 asymptotes, a vertical one, which in grade 10 is always x is equal to 0. It's the y-axis. And then a horizontal one, which is given by the Q value as it is. So y is equal to, the equation will always be y is equal to whatever that Q value is. Okay? Then I said when a is greater than 0, your function can be found in the odd number quadrants, your first and the third quadrants, according to your asymptotes, of course. That's how we define those quadrants. And then, of course, if a is less than 0, then the function is found in your even number quadrants. Okay? Then Q, apart from the fact that Q gives us the horizontal asymptote, the equation of the horizontal asymptote, it also helps us to understand the movement of the function vertically. So when Q is greater than 0, we're moving up. When Q is less than 0, we are moving down. Right? Okay. So I hope that makes sense. And I hope that's clear for all of us. Okay. Maybe I can just squeeze in the exponential function. Or did I do that one? Why do I have a feeling I did that one? Did I do the exponential function the last time? Lerat seemed to be the one that was keyed up at the last session that we had. No, we didn't. Okay. So let's look at the exponential function. Exponential function, guys. Oh, I did summaries the last time. I did like a quick summary. I think that's what I did. I kind of exposed you to the forms of the different functions so that you guys have an idea of what the different forms of the functions are. I exposed you to the forms of the different functions. That's all I did, but I didn't really go into the details of each function. All right, I just did the forms so that you can be able to identify the different forms of the functions. But your grade 10 functions, guys, are really like basic, nice, you know. It's very nice. Your functions, you can score marks, you can just destroy. Functions 100%, you can get 100% nice paper 2, their functions, especially when you understand what's going on. It's very important to understand the concept. So your exponential functions, y is equal to a b to the power x plus q. Okay. I hear you. Thank you so much, Lerado. You are very true. And those who may have missed specifically the details of the linear and the parabola function in greater detail, you can always go to my YouTube channel and check that session. It was very long though, okay, as is always the case, because there's always some preaching or sermon that happens as well. Terminations and so forth have to be taught simultaneously. Y is equal to ab to the power x plus 2. So A and B. A and B, they play a very important role in A and B in the shape and position of our function. Okay. Oh, by the way, I didn't even give you a diagram of the hyperbola function to kind of show you how it looks like. So sorry, I just wanted to do a rough here. So you remember when I said when a is greater than 0, it's supposed to be found in the first and the third quadrant. Please, guys, take note of the shape of the function. You see, This it's a nice curve, guys. It's a nice curve. It approaches the boundary line but doesn't touch the boundary line. Also, the same time here, this side, it approaches this boundary line but never touches it. Okay, because it always needs to stay within the boundaries. Guys, this is like a tiger, man. You know, the sharks and tigers, you don't want to have them going beyond the boundaries. You don't want them to recede beyond the boundaries of their habitation. They need to stay within the boundaries. Yeah, and it's also like children, actually. High school kids, they need to stay within certain boundaries and norms so that they don't lose their sense of identity. If this function was to go beyond this boundary, it loses its identity. It's no longer a hyperbola function because it cannot exist on the asymptote, for instance, this vertical asymptote, because that's where x is equal to 0. And we know 0 is in the denominator, so it cannot exist there. For the horizontal asymptote, it cannot exist there as well. Okay, so please, when you sketch your function, make sure it's a curve, you know. Yeah, then when a is less than 0, right, we know that the function is found in the even quadrants for your hyperbola. So if this is your, sorry, just excuse me for having not written horizontal dotted lines there, like, you know, spaced out, then we know that that would be a function like that. Okay, and then a function like that. You see? So I'm sure you guys can see the shape. It's supposed to be a nice smooth curve, right? Yeah, 2 arms as well, all the time 2 arms. Okay, so let's go on and move on to exponential function, because I just wanted to expose you to the sort of like what you can expect and anticipate with the diagram. Okay, so we got exponential functions. Y is equal to ab to the power x plus 2. So what I said here is that a and b tell us about the shape and the position of our function, right? Now, very important, a, there's 2 situations about a. Okay, situation number 1, a greater than 0. This means that the function is found above the asymptote. There's that word again. So are you telling me that the exponential function has an asymptote? Yes, it does actually. Exponential function has 1 horizontal asymptote. Okay, it does not have a vertical asymptote. It only has a horizontal asymptote, and rightfully so. It doesn't have a vertical asymptote because you can't see an x that's in the denominator here. So that's why we don't speak about it having a what? A vertical asymptote. Rather, it has 1 horizontal asymptote, and it just so happens that the q value is involved again in the equation of that asymptote. So that asymptote is y is equal to whatever the value of q is. So if it's 7, y is equal to 7. If it was -3, y is equal to -3. So basically this function has a horizontal asymptote. Now, when a is greater than 0, you can expect to find the function above the asymptote. Are you with me? If a is greater than 3, in other words, when a is positive, you expect to find the function above the asymptote. Okay, then when a is less than 0, in other words, when the a value is negative, don't worry, when we do examples, when you do actual problems, the asymptote will become clear to you. Okay, that's why I'm intending to do, if you're saying it's asymptotes that's confusing you, so in the examples we'll do like your functions, and then your exponential and your hyperbola function, so that you can see how we actually, because it becomes easier. Like, don't worry too much. It's a new concept, so if it's a new concept, then of course it's going to take some time. But once you get it and you grasp it and you do enough exercises around it where you actually like are able to utilize its application, then you'll be fine. Okay, So don't stress too much. I'm sorry that's confusing. I know how it feels when you are confused. So when a is less than 0, in other words, when the a value is negative, then we can expect to find the function below the asymptote. And that is very, very important. Okay. Okay. All right. Yeah. So this is very, very important. Very, very important. Okay. All right. So that's A. A has been taken care of. Then B here will now when it's above, so here's the thing. Let's say the function, this is the asymptote. So this is like case 1 of function above the asymptote. So the function can either be above the asymptote like this, okay, meaning it's an increasing function like this, right? So this is a situation where obviously a is greater than 0, but b in this situation is greater than 1. This b value that's here is greater than 1. There are two things about b. B, first and foremost, cannot be 0, and b cannot be 1. B must be, b cannot be 0 and b cannot be 1. That's two things that b cannot be for a exponential function. So first and foremost, b cannot be 0 and b cannot be 1. So there are only two situations that b can be. B can either be greater than 1 or b can be between 0 and 1. Right? So let's say this is the asymptote, and remember we are still looking at cases where the function is above the asymptote. So the function can be above the asymptote where b is greater than 1. This is the situation. This is the shape of the function that you will see. You'll see an increasing function. But if a is greater than 0 and b is between 0 and 1, then the shape of the function will still be above the asymptote. But as you can see, it will not be an increasing function, but rather it will be a decreasing function. Okay, mind you, this is case 2, right? And both these cases are cases where a is greater than 0. In other words, where the function is above the asymptote. Okay, so very important. A and b help with the shape and the position of our exponential function. Because look at a, there's a and there's b. B is the base to the variable exponent, which is x. So when a is greater than 0, I said when a is positive, we can expect to find the function above the asymptote. All right, and that means when a is greater than 0, expect this shape. If b, on the other hand, is greater than 1. When a is greater than 0, but b is between 0 and 1, the function is still above the asymptote, but instead of being a increasing function like this one, it is a decreasing function, okay, whilst it is above the asymptote. Okay, so that is scenario 1 of case 1 and case 2. Where a is greater than 0, the function, we know it should be found above the asymptote. Okay, then let's look at when a is less than 0, which we said when a is less than 0, we are expecting to find the function below the asymptote. So once again, if I sketch in my asymptote, there are two beautiful scenarios that you can expect when a is less than 0, okay, and that when a is less than 0, but at the same time b is greater than 1, then the function is like this. Okay, so the asymptote is there, y is equal to q, but because a is less than 0, the function is found below the asymptote. So that means what? It means that the function will go in this direction. Okay, that's very important. And then lastly, case 2 of when a is less than 0. That means when b is between 0 and 1. Then the function will actually be a increasing function in this way. But you see, guys, since this is an asymptote, this function will not touch this line. It will come close to the line but never touch it. It will come close to this line but never touch it. It will come close to this line, but it will never ever touch it. And then it will come close to this line, the boundary line, but it will never touch it. Because that's the thing about the asymptote. The asymptote is a boundary line where the function will never ever exist. It will never even touch that line. It will come close to it, but it will never touch. Guys, imagine an asymptote being that boy or that girl at your school that you absolutely adore and love. Like, you could absolutely say it's that person that you have your one-time all-round crush. But you know what? You know full well that pursuing that relationship at this stage of your life, especially being in high school where you are so academically driven and you have goals beyond high school, you just know that the only thing you can do is not even touch the person, for crying out loud. That person is literally an asymptote to you. You are the function. You are trying to exist and have a sense of identity, and what you don't want to do is touch what you shouldn't touch, because by doing so you would lose your sense of identity. So that's very important, making sure you don't touch the boundary line. The boundary line is not to be touched. That's the asymptote. You cannot be found there. You cannot be found existing there. You cannot, for the life of you, you can't, I have an asymptote story when I was in high school, because emotions are emotions, right? And there was a time when there was that particular person I was particularly drawn to, but I knew that academically it was not going to be safe to actually be drawing myself close to that person. So I had to make that person an asymptote and not play close to that person, and not even touch that person. Make sure that even though there's the desire, but I don't, because you know what, there was a future. And I look back on that decision. Back then it just felt like, I'm missing out. And plus, people are always telling stories at school, but you know what, it was the safe option, and I'll forever be grateful. It's kind of one of those things when I look back on and I'm just like, good memories, because I don't have a regretful story to share, about how I basically wanted to go beyond the boundary lines. So it's important to asymptotes. Just think of asymptotes as those safeguard boundary lines where you can maintain a sense of safety and not lose your identity. So an exponential function has that horizontal asymptote so that it can maintain and keep its sense of identity as an exponential function. It does not touch that boundary line. It comes close to but does not touch, and that's very important. Okay, so hope this A and B, we are able to understand, guys, that this A and B play the role of defining the shape and the position of our function. As I repeat again, when A is greater than 0, it means that the function is found above the asymptote. But when A is less than 0, it means that the function is found below the asymptote. Okay, and we've looked at the different scenarios that when A is greater than 0, but at the same time B is greater than 1, we have an increasing function, okay, because the function is found above our asymptote. But when A is greater than 0 still, meaning it's found above the asymptote, the function, but B is between 0 and 1, this is the shape of the function. This is what we can expect. Even as we sketch, we can see that when we've written down the function, that this is what we're expecting at the end. Then again, when A is less than 0, it means that the function is found below the asymptote. Okay, if it's B greater than 1 at the same time, whilst A is less than 0, we know this is the shape of the function. If B is between 0 and 1, okay, but a is still less than 0, meaning it's found below the asymptote, this is the shape we can expect. Okay, guys, I don't know if that is clear for you. And remember, the q value gives us the horizontal asymptote. The equation of the horizontal asymptote is always y is equal to this particular q value. So y is equal to whatever the value of q is. Okay, and then what does it do, this q value? It does the same thing that we had spoken about when the hyperbola is concerned. Q, when it's greater than 0, speaks to the function moving up. When q is less than 0, it speaks to the function moving down. All right, so the more we subtract to this value, it means we are moving the function further down. The more we add to this value of q, it means we're moving the function up. Okay, so hopefully we all understand. How do we find the values of a and b? So like I said, I'll be looking at specific questions now, because remember guys, all I've been doing here is I've just been explaining the concept behind the functions. Because once you understand at least the concept of the function, you see now when we get to sketching and things like that, we can always go back to the concept and ask ourselves, Kanene, what did we say when this such and such a thing happens? Okay, so let's come here. G of x is equal to 3 over x minus 1. Let's sketch the following function because we are told to do so. And we are told to indicate the intercepts with the axes and the asymptotes. Show at least 1 point on each branch. Show at least 1 point on each branch. So let's go. Let's look at how do we sketch our hyperbola. We're going to take a function at a time and we are going to sketch that particular function and see if we understand what we had just explained not so long ago. So here we have it. G of x is equal to 3 over x minus 1. Remember, g of x simply means what? Y. So we have y is equal to 3 over x minus 1. So when we have the function like that, then we can see, oh, okay, that's our y, that's our x. Then, next step, we need to plan. Guys, I like planning the sketching of my function. Okay, not just jumping into the sketch, but planning it to begin with. So first and foremost, the numerator value is 3. That means 1, a is equal to 3. In other words, a is greater than 0. What did we say when a is positive? Where did we say this function we can expect will exist? In which quadrants does this function exist, the hyperbola? Do you guys still remember? It would be so good if you guys would let me know in the comment section. Which quadrants? A is 3, meaning a is greater than 0. Okay, do you guys still remember which quadrants we said that this function would exist in? Because it helps, you know, before we even jump in, to actually have an idea. There's this concept in life that says, one of my mentors, that I have had in life once told me that when you begin something, you must begin with the end in mind. So it's like in your academics, for instance, when you begin a term, you should always have in your mind, like, what marks do I want to attain this term for this particular subject? Then you need to actually have that very clear in your head as you begin, so that you are very clear about the goals that you have and what you'd like to attain, so that the effort you put in day to day will reflect the goal that you have set and the outcome you want at the end. So it's very important to begin with the end in mind. So this is what this does. A is equal to 3, a is greater than 0. What does that mean? The function, so rough, this is a rough little thing here, rough diagram here. I know this would be my vertical asymptote, my horizontal asymptote. And already I can see x is equal to 0. My horizontal asymptote will be y is equal to -1. So I know that roughly my sketch will be like this and like that. Okay, just a rough thing, just on the side. I'm not saying draw the sketch as in like perfect. I'm just saying something just rough, so that you know in your head this is what you're expecting. And this is just a small anyana diagram, so that as I continue and proceed, everything that I will do, I have this in mind. This is what I want to see at the end. All right, does that make sense? I hope you understand what I mean. So when you look at this value that's in the numerator and you know what it is and you know what it means for the function, then you can actually have a rough plan there. You can just do this in rough, small anyala pencil thing in magic, so that you see what you have. 2. So what are the vertical asymptote and the horizontal asymptote equations? Because remember, when I have those, then I can go ahead. Okay, so my vertical asymptote, what is the equation of the vertical asymptote for this function? The equation of the vertical asymptote. And what is the equation of the vertical asymptote? Vertical asymptote and the horizontal asymptote. So let's start with the vertical asymptote. The equation of the vertical asymptote, where this is concerned, do you remember where we look for our vertical asymptote? Okay, you can see Moss, and we said this is always going to be the value in grade 10 all the time, so we don't even have to worry about it. Our vertical asymptote here will be x is equal to 0, guys. All right, because we know that in the denominator x cannot be 0. Then the horizontal asymptote, it will be y is equal to -1. Okay, so I know now my boundary lines. Then 3, 2 things. You need your x-intercept, which is when you let y be equal to 0, right? You need your x-intercept, okay? And then we don't bother ourselves here and find the y-intercept, because you don't remember, if we say we are finding the y-intercept, we know that if we let x be equal to 0, the fraction will be undefined. Okay, that's for our grade 10 syllabus. So we don't bother ourselves. We don't find y-intercept. Why don't we do that? Because the vertical asymptote, all right, that's where the function is not found. So we can't expect to find the function cutting through the y-axis. Okay, we don't find y-intercept in grade 10. All right, don't waste your time. Okay, right, so let's go ahead. We have 1, 2, we just need the x-intercept. So let's let y be equal to 0. Let's go and write this. Y is equal to 3 over x minus 1. We let y be equal to 0. Substitute that quickly. Hello guys, did you miss this part about the x-intercept? Okay, I'll repeat, it's fine. All right, so just from the top again, we started out by planning. We look at the numerator value 3, a is equal to 3. We look at that numerator value because we see that the function is in the form. Okay, no, this is not a quadratic, it's a hyperbola function. Remember, the function form is g of x is equal to 3 over x minus 1. So the 3 over x minus 1, remember, when the x is in the denominator, this is a hyperbola function. Okay. So y is equal to 3 over x minus 1. The a value, the numerator value is 3. And this 3, a is greater than 0, guys. A is greater than 0 because a is equal to 3. When a is equal to 3 and a is greater than 0, we said that the function can be found, because it's a hyperbola, can be found in the third and the fourth quadrant. So I said in rough, you just sketch, okay,